Welcome back to part two. In part two, we're going to continue, and we're going to apply calculus to determine the electric field that comes from the line segment at point P. Okay. So I'm going to start off by writing an expression for the net electric field. Of course, that's a vector. And when I write this, I'm going to anticipate that I'm going to have account for the x component in the I-hat direction, and I'm going to have to account for the y component of the field in the j-hat direction. So the electric field is a vector, and so it's going to have these two components to it, and we're going to basically treat them separately and see if we can come up with an answer separately. Okay. All right, so the first thing I'm going to do is the easiest thing. I'm going to make an assertion. I'm going to say something. I'm going to say this. I'm going to say that if you add up all of the y components, okay, if I were to basically do an integral of all the y components, that would be equal to 0. So that's the integral sign there, and if I add up all of these DEYs, they should be 0. Now, everybody remember that DEY in this picture is just from this one particular situation. But when my charges, if I consider a charge that's, say, down here, right there, this DQ, I hope you can see that that electric field would kind of come up this way, and its component, its y component, would cancel the y component from my first picture. And my point would be for any DQ that you can imagine on the top half of the line, there's going to be a corresponding DQ on the bottom half which cancels, where the electric fields cancel. So what we say in physics is that when this happens, you can say, well, that cancels out to 0, and the argument we use is we say by symmetry. And we're going to use that argument again, and so that phrase is super important that you know what that means. Okay. So by symmetry, that goes away. So all we have to really do in this problem is figure out what's the x component, because that clearly does not go away. Okay. So our game is going to be to get this, and I'm going to set up an integral here, and I'm going to say that the total here has to come from all of the pieces that add up. Just like we said here, they add up to 0. We're going to say here they're going to add up to something, but it's not going to be 0. All right. So now we have to work in the details. All right. So the first thing I'm going to do is I'm going to replace the DEX. I'm going to come up to my picture, and I see it here. DEX is this x component, and I know that I can get it from DE by multiplying by the cosine. Okay, so cosine theta, there it is. I'm talking about this right triangle up here. And so I can find the x component by multiplying this vector times cos theta, and then I'm going to add up all of these things to determine the total electric field in the x direction. Okay. Next step, I'm going to replace DE with something that we all know from last week, which is the electric field here from a point charge is simply equal to K dQ over R squared. That's my DE. That's this term. All right, so again, it's our assumption that we have a point charge up here, dQ, which is causing that electric field. Now, the second thing I'm going to do might seem a little bit tricky to you the first time I show you, but I'm not going to write cosine theta anymore because I don't like having so many variables. And I want to get my variables more in terms of the length variables in the picture. So instead of writing cos theta, I'm going to remember my SOHCAHTOA, right? And I'm going to remember that cosine is adjacent over hypotenuse. So if I come up to this big right triangle, my adjacent side is x, and my hypotenuse is r. I'm going to replace cos theta with x over r. And please be okay with that, because remember, trig functions are nothing other than ratios of sides on a triangle. We're going to do that type of substitution plenty. So of course, when we have this now, we're going to end up with k x dq over r cubed integral. And then I'm going to have to solve that integral. Okay. Now, at this point, you might be thinking, oh, this is easy, because all I have to do is factor out k and x and r cubed and bring them out, and then integrate dq to get q. After all, we did that for the ring of charge. But you cannot do that here, because as you select different dq's, the r is going to change. The x is going to change. And so you have kind of like moving parts here that you have to worry about. So when you're moving up and down this line and taking different dq's in the integral, you're also changing variables in here. And we need to have a way to deal with that. So you cannot factor out x and r cubed. So cannot take out x or r cubed. It's important. And so we're going to need to do a substitution here, and we're going to need to eliminate dq and replace it with something maybe that would be more useful to us. Okay. I made a little mistake here, and I just caught it myself. I'm going to say that I'm going to cross this out here and say that you can't take out the r cubed. And my mistake was that the x value is not changing here. This x is constant. So sorry about that. But the x value doesn't change. The r value does. Okay. So we still have to do this though, because we can't take out that r cubed. So we need to do a substitution here. All right. So let me go ahead and write this again. So we'll factor out the k and the x. All right. Now for r cubed, I'm going to use Pythagorean theorem. I know that r is going to be equal to x squared plus y squared to the 1/2. Then I have to cube that because of that cube that's there. Okay. And again, my x doesn't change, but my y does. So up on the top, I'm going to need to do some type of a substitution here, maybe that involves y instead of dq, because I want my integral to deal with the y values. So at this point, I will go back up to my statements up here, and I'm going to use them. So coming back up here, when we talked about the local density, we said that dq over dy is equal to overall charge divided by overall length. And so my substitution is going to be to isolate dq and rewrite it in terms of dy. And so I'll write it, and then you can hopefully see why this is a great thing. So again, I'm simply substituting. I'm kicking out dq, and I'm replacing it with the substitution that's over here. And the advantage to that is that I now have the integral in terms of dy, and I have y that's in the integral, and so I can actually go and evaluate, which is what I want to do. All right, so the last step I'm going to take here in this video is I'm just going to kind of simplify things out. Q over 2a can come out. So I have kxq divided by 2a. And then my integral is going to be dy over x squared plus y squared to the 3/2 power, right? By math. And because my integral is in terms of dy, I can run from negative a to positive a for my endpoints. And so now I have an integral that I can actually evaluate and get to my answer. So I'm going to stop the video here. We'll do one more part, and I'll show you how to evaluate this, and then we'll look at the solution and see if it makes sense.